Okay, so just like single replacements, the first set of videos that I put up about double replacement, they're just sort of they give you basic, but then, we need to expand on these as well, so we can get more information from the chemical reactions and also talk more about the reactions taking place. Right. So, just like single replacements, we're going to predict if they actually take place, but now instead of the activity series, we're going to use the solubility table. Then we're going to write the equation again with all its states. We're going to write an equal ionic equation and then a net ionic equation. We won't be writing half reactions. The net ionic equation will tell us what we need to know about the equation. As in single replacements, not every scenario will work. The reason chemical reactions take place is that there is something that drives the reactions to become product. For a single replacement and combustion reaction, the thrust of the reaction is oxidation and reduction. So gaining and losing of electrons. So one substance has the ability or desire sort of to gain electrons, and the other substance will give. However, in double replacement, the driver of the reactions is not essentially oxidation reduction, it's change in state. Okay, this is where you start out with one state. Okay, in this case, it's going to be aqueous, even though it's not a state, it's still a unique system. And then you get a formation of a solid when you combine the two reactants. And this forces the reaction. Now, if you take 122, we'll talk about why this forcing causes the reaction to take place. So for double replacement reaction, there are a couple of rules that determine if a reaction will take place. The first rule is actually both the reactants have to be soluble. Ion compounds have to be soluble. And we actually have to, that should be in the, for single replacement as well, the ionic compound has got to be soluble. Not all ionic compounds are equally soluble. And again, if you take 122, we'll get more into that. And really, the most important one here is one of the products has to be insoluble. That means it comes out of solution. It's no longer, it's what you'll end up is that you end up with a heterogeneous mixture. Okay, so how do we do this? How do we determine if a chemical reaction is going to take place? A double replacement. We're going to use something called a solubility table. And here's an example of a solubility table. What this table says is that anything combined with group 1 or column 1 or any negative ion that combines with the column 1 or ammonium. Okay, so you're going to have to know ammonium is NH4 plus is soluble. Okay. Any positive ion that's connected to nitrate or acetate or perchlorates is also soluble. Usually things that are attached to halogen ions, halides, are soluble except for these guys here. And sulfates are usually soluble except with these. Okay, insolubles, hydroxides and sulfides are insoluble except with the group 1, which is said over here. And these guys, carbonates and phosphates, are insoluble except when they're with these guys. So what I would suggest, instead of reinventing the wheel about all this stuff, just there's tons of videos on this. So here's one you can just take a look at, show you how to use it. The solubility table. This will be available to you when you're doing tests or homework. So let's move forward with it. So let's try a couple. So sodium carbonate added to calcium nitrate. Well, let's first make sure that both of these are soluble. So if you go back and look at the solubility table, you'll see anything with sodium is soluble, anything with nitrate is soluble. So right off the bat, my first rule that the both reactants are soluble is satisfied. Right now, my products, one of the products has to be insoluble. So so my product is going to be sodium nitrate and calcium carbonate. Okay, now one of these has to be insoluble. Okay, so again, anything with sodium, and actually anything with nitrate is soluble. So sodium nitrate is soluble. But how about the calcium carbonate? Okay, if you go back and look at the solubility table, you'll see anything, well, most carbonates are insoluble, especially with calcium, so this is insoluble. So this reaction will take place, and so let's take a look at it. So what we're going to get is sodium carbonate, aqueous, calcium nitrate, aqueous, so we'll yield aqueous sodium nitrate plus solid calcium carbonate. And we'll look at that in a minute. So let's look at a reaction that probably won't happen, okay? So potassium chloride plus magnesium acetate, first of all, are they both soluble? Yes, they are. I can go back and look. Anything with potassium and anything with acetate are soluble, so both are soluble. How about your products? Well, your products are going to be potassium acetate and, potassium acetate and magnesium chloride. Right, one of these guys has to be insoluble. So if you look at the chart, you'll see that potassium acetate is soluble. Potassium acetate are soluble with anything. How about magnesium chloride? Yes, magnesium chloride is also soluble. Okay, so it's soluble. So this reaction will not happen, and we'll take a closer look at it why it doesn't. So let's go back and look at the first reaction and see how to write it up. So first of all, write out the word equation: sodium carbonate, aqueous. You can do this instead of writing aqueous sodium carbonate. You can write sodium carbonate AQ. Calcium nitrate AQ gives me sodium nitrate AQ and calcium carbonate solid. You don't have to capitalize these substances. Sometimes I do, sometimes I don't. All right, the balanced equation. So I'm just going to write down what I have: sodium carbonate. So sodium is Na plus, carbonate is CO3 2 minus. So I need two of them. All right, so I'm not balanced equation, I'm just getting my formulas right. Calcium nitrate, calcium is Ca2 plus, nitrate is NO3 minus, so I need two of them. Sodium nitrate is Na plus, NO3 minus, so you don't have to add anything to it. And calcium carbonate is Ca2 plus, CO3 2 minus, and again, don't have to do anything because the superscripts are the same, the charges. Okay, next thing is balanced equation, and I'm going to start out with nitrate. I like to start out with negatives. Doesn't always work, and you can see from previous video how that is. So I'm going to get myself two nitrates. So I do that. Put 2 here. I have 2 nitrates. Now I need so step 1. Now I have 2 sodiums. I see that's good over here. Check the rest of your stuff, and everything's fine. Okay, so that's all you need to do is put a 2 here. All right, now, that's a balanced equation. Ionic equation, so this splits apart in water. So there's 2 NAs that come off, and it's CO3. The calcium nitrate. So calcium nitrate. Okay. When you put it in water, calcium splits from the two nitrates, and so you get calcium 2 nitrates. Each sodium nitrate, both of these split apart, and you do it twice, so you get 2 NAs and 2 NO3s. And this does not split apart. Okay, so don't split this apart. Okay, that's what makes this chemical reaction take place. All right, now what we do is we get rid of these spectator ions. Okay, just like in single replacement, but now we have 2 of them. So what is exactly the same on both sides? So this should be AQ down here. So I have Na, both from AQ. All right, CO3, it's a solid over here, AQ. So I gotta leave this. This is AQ, put it here, and now it's a solid, so I gotta leave that. And the NO3 is AQ on both sides, and so they cancel out. So you have 2 spectators in double replacement. And so what you're left with is carbonate plus calcium gives me calcium carbonate. All right. So no half reactions, okay, because there's no exchange of electrons. So if you notice here, there's no exchange of electrons. Everything keeps its charges. So nothing loses or gains its charges here. Na plus is still Na plus. Carbonate is 2 minus and so forth. Okay, let's do the one reaction that I said didn't work and write it out anyways and see what happens. So here's the word equation. Okay, here's the unbalanced equation. All right, so this is the balanced equation. I have 2 acetates, so I'm going to put 2 here. That doesn't belong there. Okay. All right. So, and then I need 2 CLs and 2 Ks, so I put 2 here. Okay. All right. So what happens when you just put water? The K plus and the Cl minus split apart and does that twice. The magnesium and the acetates split apart, and there's 2 acetates for every magnesium, so they split apart. So 2 of these split apart from 1 of these. Okay, so you have for the potassium acetate, each potassium splits apart from the acetate, and it does that twice. So you have 2 K pluses and 2 acetates. The magnesium, the chlorides, 2 chlorides attached to each magnesium, they split off. So you have the magnesium splits off with 2 CLs. Okay. Now, if you look at what's the same on both sides, that's same on both sides. That's same on both sides. Magnesium same on both sides. Okay. So basically what happens here is both sides are identical, exactly the same. So nothing happens. Okay. All right. So hopefully you saw how these ions split apart. So you have K plus splits from the Cl and does that twice. You have 2 of these, 2 acetates attached to magnesium. They split apart, and that only does that once. Okay, you have the K plus separating from the acetate and does that twice. And then you have the 2 Cl splitting from the magnesium, and that only happens twice. Okay, the other type of double replacement reaction that we're going to cover is the acid-base neutralization reaction. These have slightly different rules. First of all, both of the reactants have to be soluble. Second, what drives the reaction is the formation of water, not solid. This is a change in state because you're going from an aqueous system to a pure liquid. What we're going to assume is that if I give you reactants, you're going to assume the reaction takes place. Okay, so you don't have to use a solubility table for these. So here's sulfuric acid plus magnesium hydroxide, and I would strongly suggest you change in the acid to its ionic name. So hydrogen sulfate plus magnesium hydroxide. So now you can swap names. Okay, so it's going to be magnesium sulfate with hydrogen hydroxide, and hydrogen hydroxide is simply water. Okay, so here you go. Okay. Right, now, so sulfuric acid, I'll write as its ionic form. So H plus, you need 2 of them for every sulfate. Magnesium is 2 plus, hydroxide is OH minus, so you need 2 of them. So we're writing just the chemical formulas now. Magnesium is 2 plus, sulfate is 2 minus. And water I'm going to write as H plus OH minus, not H2O. This because it's easier to balance. Okay, balanced equation, I am going to start out with the negative ion that has 2. Okay, so I have 2 hydroxides, so what I'm going to do is come over here and put a 2 in front of the HOH. Alright. Okay, now I'm going to check, come over here and see I have 2 H pluses, and yes, I have 2 H pluses. Okay, and then I check the rest and I'm done. And on the previous video about double replacement, it gives you more examples of balancing equations. The ionic equation, what happens? Okay, the acid splits apart, so it's H plus 2 of them, H plus 2, SO4, 2 minus. They split apart, so you end up with 2 H pluses and SO4, 2 minus. The Mg, so you have Mg and OH. Okay, and they split apart into Mg 2 plus and 2 OHs. On this side, the magnesium and sulfate split apart, and this guy does not split apart. Okay. Right, again, don't bring this 2 down. Don't put a 2 here. Don't put the 2 here, okay? And 2 comes out front because it says you have 2 H pluses. So you get rid of the magnesium and the sulfate, and then you end up with 2 H pluses, 2 OH minuses, and water. Now, the last thing, let's take a little closer look at double replacement. In the first reaction, the net ionic equation was carbonate plus calcium yields calcium carbonate. Right, if you notice, this guy goes from a 2 minus charge to having, in a sense, no charge because it's balanced out. Okay, so in a sense, the carbonate is kind of losing its negative charge because it's getting balanced out. So it's kind of like losing electrons, losing a negative charge. It's not really losing electrons, but it's kind of losing its negative charge because it's getting balanced. So in a way, it's being oxidized. Okay. The calcium, on the other hand, looks like it's losing its 2 plus charge, which means it's becoming more negative. And when you become more negative, you become reduced. So what we get here is the carbonate looks like it's getting oxidized, and the calcium looks like it's getting reduced. Okay, now I just want to show this because essentially what it turns out that every single reaction that we talk about in chemistry essentially could be an oxidation and reduction reaction, okay, otherwise known as redox reaction. Now you don't need to know this for test, but I wanted to show you this because this is one of the cool things about chemistry. Yay! And we're going to talk more about this when we get to structure and so forth. Okay, right. So that's it for this slideshow.